Welcome to Still Science Lab. Tonight, we are going to dismantle one of the most persistent illusions in the human mind. We are going to talk about a number that is etched into the bedrock of the universe: 299,792,458 meters per second. You know this number. You were taught it in school. You see it in sci-fi movies when the starship engines glow blue and the stars stretch into lines. You know it as the speed of light. But tonight, I want you to forget that name. Calling this number the speed of light is perhaps the greatest branding error in the history of physics. It is like calling the speed of sound the speed of shouting. Yes, sound travels at that speed, but the speed of sound is a property of the air, not a property of your voice. In the same way, this cosmic limit has almost nothing to do with light itself. Light is just the most famous thing that travels this fast because it has no mass and has no choice. But if you stripped every photon out of the universe, leaving it in total, absolute darkness, this limit would still be there. It is not a speed limit for light. It is the speed limit of reality. It is the refresh rate of the cosmos. Tonight, we are going to explore why this limit exists and what the legendary physicist Richard Feynman uncovered about the texture of reality that explains why we are trapped in this bubble of causality. Feynman was not just a physicist, he was a philosopher of the absurd. He understood better than anyone that when we push nature to its extremes, whether to the microscopic scale of the atom or the macroscopic scale of the speed of light, our common sense is not just useless, it is a liability. We are evolved apes, designed to understand how to throw a rock or run from a lion. We are designed for medium sizes and medium speeds. When we look at the universe's speed limit, our intuition screams that it is wrong. Why can't I just push the gas pedal a little harder? Why can't I add 100 miles per hour to 100 miles per hour and get 200? Feynman's answer was simple, elegant, and terrifying. Nature does not care what you think is reasonable. Nature is absurd, and to understand the speed of light, we have to accept that absurdity. Let's start by stripping away the facade. Imagine you are in a car. You press the accelerator, and you go faster. You press it harder, and you go faster still. In our everyday experience, speed is additive. If you are running on a train, your speed is the speed of the train plus the speed of your legs. It feels infinite. It feels like if you just had enough energy, enough fuel, and a long enough road, you could go as fast as you wanted. You could cross the galaxy in a heartbeat. But the universe has a hard stop. There is a wall. And this wall isn't just a barrier that prevents you from moving faster. It is a barrier that prevents information from moving faster. Think of the universe not as a continuous, flowing river, but as a computer simulation. Every video game you have ever played has a refresh rate or a tick rate. It is the speed at which the processor can update the state of the world. If you shoot a virtual gun in a game, the bullet cannot hit the wall instantly. It has to travel across the pixels, frame by frame, tick by tick. The server has to update the position of the bullet, then send that information to the other player. There is a latency. The speed of light is the latency of our universe. It is the maximum speed at which one patch of space can talk to another patch of space. It is the maximum speed at which a cause can lead to an effect. If the sun were to suddenly vanish this very second, just blink out of existence, we would not know. We would not know for 8 minutes and 20 seconds. The Earth would continue to orbit a ghost. The plants would continue to photosynthesize. You would continue to see the sun in the sky, warm and bright. Why? Because the update hasn't arrived yet. The news that gravity is gone, and light is gone, is traveling toward us at the cosmic speed limit. It is rushing through the vacuum at 300,000 kilometers per second, but space is big, and the processor speed of the universe is finite. For those 8 minutes, we are living in a past that no longer exists, simply because the information cannot reach us any faster. This is the first clue that C is not about light. Gravity travels at this speed. Gluons, which hold your atoms together, travel at this speed. Gravitational waves, the ripples in the fabric of space-time itself, travel at this speed. It is the speed of interaction. It is the speed of now. Richard Feynman often spoke about the imagination of nature. He said that nature's imagination is far greater than man's, because nature never violates her own rules, no matter how complex the situation. Humans, on the other hand, try to impose our rules on nature. We want the universe to be intuitive. We want time to be a constant, universal, ticking clock that rings the same for everyone. We want space to be a fixed stage where actors move around. But Feynman, through his work on quantum electrodynamics, or QED, peered under the hood of this reality. He saw that what looks like a smooth, continuous world is actually a chaotic dance of probabilities and interactions, all governed by this rigid speed limit. Feynman realized that if you try to use common sense to understand high-speed physics, you will fail. Common sense says that if I shine a flashlight from a moving train, the light should go faster. It doesn't. Common sense says that two events happening at the same time for me are happening at the same time for you. They aren't. Feynman embraced this absurdity. He argued that we must be humble. We must look at the experiments, look at the math, and accept the result, no matter how much it melts our minds. The speed of light is the ultimate test of this humility. It forces us to accept that time is not rigid. Space is not rigid. The only thing in the universe that is rigid, the only thing that you can trust, is this speed limit. Why is this limit here? Why isn't the processing speed infinite? If the speed of light were infinite, the universe would be a vastly different and likely impossible place. If information could travel instantly, then every point in the universe would be connected to every other point simultaneously. There would be no here and there. There would be no before and after. Cause and effect would collapse. In a universe with infinite speed, everything would happen at once. The existence of a limit is what gives us the structure of time. It separates the past from the future. It creates the light cone that defines your reality. You can only affect things that light can reach, and you can only be affected by things that light has reached. You are trapped in a bubble of causality, and the walls of that bubble are expanding at the speed of light. This brings us to the core of what we will uncover in this series. We tend to view the speed limit as a prison. We look at the stars, Alpha Centauri, the Andromeda Galaxy, and we feel trapped because it would take years or millions of years to reach them. We curse the speed of light for keeping us grounded, but Feynman's work suggests that we should look at it differently. The speed limit is not a prison wall. It is the scaffolding that holds reality together. Without it, matter could not exist. Atoms would not be stable. The electromagnetic forces that hold your body together rely on the exchange of photons, and the rules of that exchange are dictated by this speed. If you change the number, even slightly, the delicate balance of the universe unravels. When Feynman looked at the behavior of light and matter, he saw a universe that was deeply, fundamentally weird. He developed a way of looking at particles, Feynman diagrams, that suggested things that shouldn't be possible, like particles traveling backward in time. But these strange behaviors are only possible because of the relativistic framework Einstein built and Feynman expanded upon. The speed of light is the pivot point. It is the fulcrum upon which the seesaw of space and time balances. If you push space, time pushes back. If you move fast through space, you move slow through time. The sum of your motion through space and time is always equal to the speed of light. This means that, in a poetic sense, you are already traveling at the speed of light. We all are. We are mostly traveling through time, and a little bit through space. When we speed up in a car, we divert some of that velocity from time into space. We age a tiny bit slower. We twist the knob of reality. So, as we embark on this journey into the mind of Feynman and the geometry of Einstein, discard your intuition. Leave your common sense at the door of the laboratory. It will not help you here. We are going to look at the machinery of the cosmos. We are going to see why you cannot push an object to light speed, not because you lack the engine power, but because the universe physically conspires against you by turning your energy into mass. We are going to see how light doesn't just travel in a straight line, but takes every possible path in the universe simultaneously. And we are going to understand that 299,792,458 meters per second is not a measurement of speed. It is a measurement of the grain of existence. It is the pixel size of reality. It is the resolution of the universe, and it is the only thing standing between us and total chaos. Welcome to the limit. To understand why the universe has a speed limit, we must first understand the civil war that tore physics apart in the late 19th century. Before we knew about relativity, before we understood the quantum realm, and before we accepted the bizarre nature of time, the world was governed by the iron laws of Isaac Newton. For over 200 years, Newton was the undisputed king of reality. His laws of motion and gravity were not just theories. They were seen as the divine architecture of the cosmos. They explained everything from the falling of an apple to the precise orbits of the planets. They allowed us to build steam engines, bridges, and the industrial world. Newton's universe was a clockwork mechanism, predictable, rigid, and deeply intuitive. It was a world that made sense to the human mind because it matched our everyday experience. At the heart of Newton's universe was a concept so simple that we take it for granted: the idea that speeds add up. This is known as Galilean relativity. Imagine you are standing on a train platform. A train rushes past you at 100 miles per hour. On that train, a pitcher throws a baseball forward at 100 miles per hour. To the pitcher on the train, the ball is moving at 100, but to you, standing on the platform, the ball is moving at 200 miles per hour. You simply add the speed of the train to the speed of the ball. It is basic arithmetic. It is logical. If you had a fast enough rocket and you launched a missile from that rocket, the speeds would stack. In Newton's world, there was no limit. If you kept adding energy, you kept adding speed, potentially all the way to infinity. Time was a constant background drumbeat, ticking the same for the pitcher, the passenger, and the observer on the platform. Space was a fixed stage. The players moved, but the stage remained still. But in the mid-1800s, a quiet, modest Scotsman named James Clerk Maxwell accidentally started a revolution that would destroy Newton's clockwork. Maxwell was not trying to overthrow the government of physics. He was simply trying to understand electricity and magnetism. At the time, these were seen as separate, somewhat mysterious phenomena. Maxwell, through a stroke of mathematical genius, realized they were two sides of the same coin. He unified them into a set of equations that described how electric and magnetic fields dance together. He discovered that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. They feed each other, creating a self-sustaining wave of energy that can travel through empty space. When Maxwell calculated the speed of this theoretical wave, a specific number fell out of his equations. That number was approximately 300,000 kilometers per second. Maxwell instantly recognized it. It was the speed of light. He had made a discovery that changed human history. Light is not just brightness. Light is an electromagnetic wave. But hidden inside this triumph was a terrifying contradiction. Maxwell's equations provided a fixed speed for light, but they did not say relative to what. In Newton's physics, speed is always relative. A car moves at 60 miles per hour relative to the road. The baseball moves relative to the train. But Maxwell's equations didn't have a variable for the observer. They didn't care if you were standing still, running, or riding a rocket. The math simply stated, light travels at c. This innocent-looking fact was a declaration of war against Newton. Let's apply Newton's logic to Maxwell's light. Imagine you are on a supertrain moving at half the speed of light. You turn on a flashlight and shine it forward. According to Newton, the light should leave your flashlight at the speed of light, but to an observer on the ground, that light should be moving at 1.5 times the speed of light. You add the speeds, but Maxwell says no. Maxwell says the observer on the ground sees the light moving at exactly the speed of light, and, even more confusingly, you on the train also see it moving away from you at exactly the speed of light. This is where the cracks began to form. How can two people, moving at vastly different speeds, measure the same beam of light moving at the same speed? It seems physically impossible. It violates the basic arithmetic of 1 + 1 = 2. The situation gets even worse when you imagine chasing a beam of light. This was the famous thought experiment that haunted a young Albert Einstein. If Newton is right and speeds add up, then you should be able to accelerate a spaceship until you are moving alongside a beam of light matching its speed perfectly. If you did this, and you looked over at the light beam, what would you see? According to Newtonian logic, you should see the electromagnetic wave frozen in space next to you, like a stationary ripple in a frozen pond. But according to Maxwell, this is impossible. Light is a wave of changing fields. The electric field must change to create the magnetic field, which must change to create the electric field. It is a shark that must swim to survive. If you freeze it, the induction stops. The wave vanishes. So, Maxwell's equations say you can never catch light. You can never see a frozen wave. The laws of electromagnetism demand that light is always moving at c, no matter how fast you chase it. By the late 19th century, physics was in a state of quiet panic. You had two monumental pillars of science, Newton's mechanics and Maxwell's electromagnetism, and they were mutually exclusive. They could not both be true. If Newton was right, Maxwell's equations were wrong, and electricity shouldn't work the way it does. If Maxwell was right, Newton's laws of motion were wrong, and our understanding of the entire physical world was flawed. The scientific community tried desperately to patch this hole. They invented a substance called the luminiferous ether. They suggested that the universe was filled with this invisible, stationary fluid. They argued that Maxwell's speed of light was only constant relative to the ether, not to us. This would save Newton. It would mean that if we moved through the ether, we would see light travel at different speeds. It was a clever fix, a way to keep the old world alive. But nature refused to cooperate. Every experiment designed to detect the ether failed. When they measured the speed of light in the direction of Earth's orbit and against it, they expected to see a difference, a wind of ether blowing past us. But there was no wind. The speed of light was stubbornly, relentlessly the same every single time. This was the crisis. The data was undeniable. The speed of light was constant. Maxwell was right, but the implications were too radical for most to accept. If the speed of light is constant for everyone, regardless of their motion, then the speed part of the equation is fixed. Speed is simply distance divided by time. If the answer speed must always be the same, then the variables, distance and time, must be the ones that change. This is the realization that broke the universe. To save the laws of physics, we had to sacrifice the stability of space and time. We had to accept that 1 second is not a universal unit. 1 second for you might be 2 seconds for me, depending on how fast we are moving. We had to accept that 1 meter is not a fixed length. Space itself must scrunch up and compress to accommodate the constant speed of light. The speed limit, therefore, is not an arbitrary number. It is not a traffic rule imposed by a cosmic police officer. It is the necessary glue that keeps the laws of physics consistent. If light speed were not the limit, if speeds could add up indefinitely as Newton thought, then Maxwell's equations would collapse. Electromagnetism would fail. Atoms would not hold together. The causal structure of the universe would dissolve. The war between Newton and Maxwell revealed that our common sense is a local illusion. In the grand scheme of the cosmos, rigidity is a myth. Space and time are flexible, malleable, and soft. The only thing that is hard, the only thing that is truly solid, is the speed of light. This historical conflict established the why of the limit. It wasn't discovered, it was demanded by the mathematical consistency of reality. We live in a universe where the laws of physics must be the same for all observers. Whether you are sitting on a couch or flying in a spaceship, the laws of electromagnetism must work the same way. You must be able to switch on a light and have it work. For that to happen, for the laws of physics to remain democratic and universal, the speed of light must be the absolute dictator of motion. It is the invariant constant that forces everything else, your time, your length, your mass, to bend around it. The limit exists to save the universe from logical contradiction. It is the peace treaty that ended the war, but the terms of that treaty were that we could never, ever go faster. The resolution to the war between Newton and Maxwell, the solution that saved physics from collapsing into a paradox, came from the mind of a 26-year-old patent clerk who had no laboratory, no expensive equipment, and no academic prestige. Albert Einstein did not discover the truth about the speed limit by smashing atoms or measuring stars. He discovered it by closing his eyes and playing a movie in his head. He built a mental apparatus, a simple machine of logic that we will call the Einstein Box. This thought experiment is the key to understanding why time is not a universal constant, and why the speed of light is the rigid backbone upon which the floppy, flexible flesh of space and time hangs. To understand the limit, we must step inside this box and watch the geometry of the universe distort before our eyes. Imagine the simplest clock possible. Forget gears, springs, and digital displays, as those are just mechanical devices that can break or fail. We need a fundamental clock, one built from the laws of physics themselves. Imagine 2 perfect mirrors placed parallel to each other, one on the floor and one on the ceiling. Between them, a single particle of light, a photon, bounces up and down. Every time the photon hits the bottom mirror, the clock ticks. Tick, tock, tick, tock. The time it takes for the photon to travel from the floor to the ceiling is 1 unit of time. This is our light clock. It is the heartbeat of a stationary reality. Now, imagine you are holding this clock while standing on a train platform. You watch the photon bounce. It travels in a straight vertical line, up, down, up, down. The path is short, direct, and efficient. The distance the photon travels is simply the height of the mirrors. Now, let's introduce motion. Imagine a futuristic train whizzing past the platform at an incredible speed, let's say 50% of the speed of light. On this train, there is a passenger holding an identical light clock. Here is the crucial moment where intuition dies and relativity is born. We must look at the passenger's clock from two different perspectives. First, consider the passenger on the train. To them, the train is not moving. The platform is moving. Inside their cabin, everything feels normal. They look at their clock, and they see the photon bouncing straight up and down. Up, down, up, down. To the passenger, the laws of physics are behaving perfectly. The light travels the vertical distance, and the clock ticks at a normal rhythm. But now, switch back to your perspective on the platform. You are watching the train streak across the landscape from left to right. As you look through the window at the passenger's clock, you do not see the photon moving in a straight vertical line. Why? Because the mirrors are moving. In the time it takes for the photon to leave the bottom mirror and reach the top mirror has moved sideways to the right. The photon cannot just go up. It has to move up and over to catch the mirror. Trace the path of that photon in your mind. It leaves the bottom mirror, travels diagonally upward to hit the top mirror, and then travels diagonally downward to hit the bottom mirror again. Instead of a straight vertical line, the light is tracing a sawtooth pattern. It is drawing a series of triangles. If you remember your high school geometry, you know that the diagonal side of a triangle, the hypotenuse, is always longer than the vertical side. This is an undeniable geometric fact. The path the photon takes on the moving train is physically longer than the path the photon takes in your stationary clock. Now we arrive at the trap. We have a longer distance. In a Newtonian world, this wouldn't be a problem. If you throw a ball diagonally, it just speeds up to cover the extra distance in the same amount of time. If distance increases, speed increases to compensate. But we are living in Maxwell's world. We are living in a universe where the speed of light is the law. The photon on the moving train cannot speed up. It is traveling at exactly c, the same speed as the photon in your stationary clock. Look at the equation. Speed equals distance divided by time. We have a problem. The speed must stay the same. The distance has unquestionably increased because the diagonal is longer than the vertical. Mathematically, there is only one variable left to change. If the numerator, distance, gets bigger and the result, speed, stays the same, the denominator, time, must get bigger. This is not a trick of the eye. This is not a mechanical error. This is a fundamental restructuring of reality. For the speed of light to remain constant, the duration of a second on the moving train must expand. Time itself must slow down. When you watch the clock on the moving train, you see the photon struggling to cover that longer diagonal path at its fixed speed. It takes longer to complete one tick. You measure the intervals, and they are dragged out. While your clock goes tick, 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 the moving clock goes tick, tick, tick. This phenomenon is called time dilation. It means that time is not a fixed backdrop. It is a flexible resource. The universe is performing a cosmic exchange. To allow the train to move through space, it must steal some velocity from its movement through time. The faster you move through space, the slower you move through time. The speed of light acts as the conversion rate. It is the strict banker that ensures the account balances. You cannot have maximum speed in space and maximum speed in time simultaneously. The total velocity through space-time must always equal c. If you divert all your arrow's length into spatial movement, approaching light speed, you have almost nothing left for temporal movement. Your time freezes. This shattering of absolute time explains why the limit feels so counterintuitive. We feel like we should be able to push harder and go faster, but we are fighting against the geometry of the universe. The faster the train goes, the more stretched that diagonal path becomes. As the train approaches the speed of light, the triangle becomes incredibly long and flat. The photon has to travel a massive horizontal distance just to make a tiny vertical tick. The path approaches infinity. And since the photon can only move at c, the time it takes to complete that tick approaches infinity. If the train could actually reach the speed of light, the photon would never reach the top mirror. It would be chasing it forever, parallel to the floor. The clock would stop. Time would stand still. This is why you cannot break the limit. It isn't just that you can't go faster. It's that the very mechanism of change, the ticking of the clock, the beating of your heart, the firing of your neurons grinds to a halt as you approach the barrier. This Einstein Box reveals that space and time are not the rigid stage Newton imagined. They are more like a block of rubber. The speed of light is the steel rod running through the rubber. You can twist the rubber, stretch it, and compress it, but the rod remains straight. When we move fast, we are twisting the rubber. We are stretching space and compressing time to accommodate the unyielding rod of light speed. This has profound implications for our existence. It means that there is no universal now. Now is a local illusion. What is happening now for you is different from what is happening now for someone moving at high speed. If an astronaut travels to a distant star at 99% of the speed of light, they are living in a different temporal reality. Their triangles are stretched, their clocks run slow. They might age only 1 year, while everyone they love on Earth ages a century. They haven't traveled through time in the sci-fi sense. They have simply taken a different geometric path through space-time. They took the hypotenuse. We took the vertical line. The Einstein Box teaches us that the speed limit is not really a limit on speed. It is a statement about the relationship between space and time. It tells us that they are interchangeable. They are made of the same stuff. And the conversion factor, the exchange rate between a meter of space and a second of time, is exactly 299,792,458. This is the rigid backbone of the cosmos. Everything else, your size, your age, the color of the stars, is relative. It changes depending on who is looking. But the speed of light is the one absolute truth. It is the invariant. It is the anchor. By forcing light to be constant, the universe forces us to be flexible. We are the ones who shrink. We are the ones who slow down. We are the variable in the equation. We tend to think of ourselves as the constant observers of the universe, but relativity tells us we are just jelly, squishing and stretching as we move, all to protect the sanctity of that one specific number. So, when we ask, why is light speed the limit? The answer from the Einstein Box is, because if it weren't, time wouldn't work. The limit is the price we pay for having a universe where cause follows effect, where electricity flows, and where the laws of physics are consistent. We are trapped in the slow lane because we are massive beings living in a geometric reality defined by the path of a massless photon. We are slaves to the hypotenuse, and as we will see, this geometric trap gets even tighter when we try to push mass against the wall of energy. The box shows us why time slows down, but it doesn't fully explain why we can't just power through it. For that, we need to look at the weight of energy itself. We need to understand the prison of infinite mass. We have explored the geometry of space and the elasticity of time, seeing how the universe conspires to bend reality to keep the speed of light constant. But there is a more visceral, mechanical reason why you, as a physical being, can never break this limit. It is not just about clocks slowing down or lengths contracting. It is about the very substance of your existence. It is about the weight of energy itself. We often think of the speed of light as a rule, like a speed limit sign on a highway that says, "Do not pass." But it is more than a rule. It is a physical barrier built out of the fundamental relationship between matter and energy. It is an infinite wall, and the bricks of this wall are made of your own kinetic energy. To understand why we are trapped below this ceiling, we must look at the most famous equation in human history, an equation that is often quoted but rarely truly felt. E equals mc squared. For decades, pop culture has taught us that this equation is about nuclear bombs. It tells us how a tiny amount of mass, like a lump of uranium, can be converted into a massive amount of energy. And while that is true, it is only half the story. The equals sign in algebra is a two-way street. If mass can become energy, then energy can become mass. This is the secret mechanism of the cosmic prison. It means that mass and energy are not two different things. They are the same entity wearing different clothes. Mass is just condensed, frozen energy. Energy is just liberated, fluid mass. They are the same currency, exchangeable at the bank of the universe, and the exchange rate is the speed of light squared. So, let us take this concept and apply it to a spaceship trying to break the record. Imagine we have built the ultimate machine, a starship with an engine that can provide thrust forever. We have an infinite fuel tank. We line up on the cosmic runway and we ignite the engines. According to Isaac Newton, this should be simple. Newton's second law states that force equals mass times acceleration. If our mass is constant, the ship, and our force is constant, the engine, then our acceleration should be constant. We should pick up speed at a steady rate, 0 to 60, 60 to 100, on and on. In Newton's world, if we push long enough, we will eventually cross the 300,000 kilometers per second mark. There is nothing in the math to stop us. But Newton was wrong about one crucial assumption. He thought mass was constant. He thought that a kilogram is a kilogram is a kilogram, whether it is sitting on a desk or flying at the speed of sound. Einstein revealed that this is an illusion. As our spaceship accelerates, we are pouring energy into it. We are burning fuel, creating thrust, and transferring that kinetic energy into the frame of the ship. At low speeds, the speeds of cars and jets, the amount of energy is negligible compared to the mass of the ship, so we don't notice anything strange. But as we approach the relativistic realm, something bizarre begins to happen. The energy we are pumping into the ship has to go somewhere. It cannot just disappear. It becomes part of the ship. And because energy and mass are equivalent, that kinetic energy exhibits its own gravity. It exhibits its own inertia. As we speed up, the ship actually gains relativistic mass. It becomes heavier, not in the sense that it gets bigger or grows more atoms, but in the sense that it becomes harder to push. The m in Newton's equation begins to climb. Imagine you are pushing a shopping cart. At first, it is empty. You push it, and it accelerates easily. But imagine that for every step you take, someone drops a brick into the cart. The faster you go, the more bricks appear. You have to push harder just to maintain your acceleration. Now, imagine that the faster you go, the heavier the bricks become. This is what happens as you approach the speed of light. The energy of your own motion acts like lead weights dragging you back. At 10% of the speed of light, the effect is barely noticeable. The ship is only a tiny fraction of a percent heavier. We push on. We hit 50% of light speed. The engines are roaring, but the acceleration is starting to lag. The ship is resisting the push more than it should. We are fighting against our own momentum, but we are stubborn. We throttle up to maximum power. We hit 90% of the speed of light. Now, the situation is becoming critical. The ship is effectively twice as heavy as it was when we started. Our engines are working twice as hard just to give us the same nudge. Then we hit 99% of the speed of light. At this point, the curve of reality shoots upward. We are no longer climbing a gentle hill. We are climbing a vertical cliff. Every ounce of energy we pour into the engines is almost entirely converted into mass, not speed. We are burning the energy of entire stars, pumping it into the drive, but the speedometer barely twitches. We inch from 99.9% to 99.99%. The ship is now massive, metaphorically weighing as much as a planet, then a star, then a galaxy. The more we push, the heavier it gets. The heavier it gets, the harder it is to push. It is a cosmic feedback loop, a trap designed by the laws of physics. This leads us to the ultimate realization. To reach 100% of the speed of light, to actually hit that magic number, the mass of our spaceship would become infinite. And to move an object with infinite mass, you would need infinite energy. Infinite energy does not exist. There is not enough energy in all the stars, all the black holes, and all the radiation in the entire observable universe to push a single electron to the speed of light. It is mathematically and physically impossible. The universe runs out of fuel before you reach the limit. This is the infinite mass prison. We are trapped below the speed of light, not because our engines are too weak, but because we are made of matter. Matter is, by definition, something that resists motion. It has inertia, and relativity tells us that inertia is not a fixed number. It is a dynamic beast that grows the faster you feed it speed. The speed of light is the asymptote, the line on the graph that the curve approaches forever but never touches. You can get to 99.999999% if you have enough energy, but there will always be a tiny sliver of speed you cannot close, protected by a wall of infinite weight. This explains the fundamental difference between us and light. Why can light travel at light speed? Because a photon has no mass. It has zero rest mass. It carries no baggage. Because it weighs nothing, it essentially has to travel at the maximum speed. It has no inertia to hold it back. It is born at the speed limit, and it dies at the speed limit. It never accelerates, and it never slows down. For a photon, there is no transition, but for us, for protons, electrons, spaceships, and humans, we are burdened by our substance. We have mass. That mass is our anchor to the slow lane. This mechanism is not just a theory, we see it every day in our particle accelerators. At the Large Hadron Collider in Geneva, we smash protons together at 99.999999% of the speed of light. To get them that fast, we use massive magnets and incredible amounts of electricity. As those protons circle the ring, they become thousands of times heavier than normal protons. The magnets have to adjust their strength precisely to hold these heavy protons in place. If the math of relativity were wrong, the protons would crash into the walls of the tunnel instantly. The fact that the machine works is proof that mass increases with speed. We are literally creating heavy matter out of pure kinetic energy, verifying Einstein's prison with every collision. The concept of the infinite mass prison changes how we view our place in the cosmos. It implies that the universe is strictly segregated. There is the realm of the massless, the photons, the gluons, the gravitational waves which live at the ceiling of reality, zipping around at the speed of causality, timeless and free. And then there is the realm of the massive us. We are the slow, heavy giants, trudging through the mud of space-time. We can look up at the ceiling, we can approach it, but we can never touch it. Our very nature as physical beings prevents it. To be matter is to be slow. To have structure is to have limits. But there is a beauty in this prison. If we could reach the speed of light, our mass would become infinite, and we would likely collapse into a black hole, destroying ourselves and everything around us. The limit saves us from our own energy. It prevents any single object from dominating the universe with infinite momentum. It keeps the cosmos stable. The wall of infinite mass is not just a barrier, it is a guardrail. It ensures that while we can dream of the stars, we must journey to them with patience, dragging our heavy, beautiful existence through the fabric of space, forever chasing the light but never catching it. This mechanical reality sets the stage for the next layer of the mystery. We know why we can't go faster, but to understand what light actually is and how it navigates this limit, we must leave the world of massive ships and enter the bizarre, probabilistic world of Richard Feynman and quantum electrodynamics. We must look at how the speed of light dictates the dance of the subatomic world. We have seen how the speed of light acts as a prison wall for matter, a barrier of infinite mass that keeps us grounded in the slow lane of the universe. But now we must leave the world of heavy, clunky objects, spaceships, planets, and particles, and turn our attention to the prisoner that lives on the wall itself, light. If we are trapped below the limit, light is trapped at the limit. And while we might think we understand how light moves in straight lines, bouncing off mirrors like billiard balls, Richard Feynman showed us that this is a comfortable illusion. The truth of how light navigates the cosmos is far stranger, far more absurd, and it reveals that the speed of light is not just a velocity, but the fundamental clock rate of quantum reality. To understand this, we must dive into the theory that Feynman called the jewel of physics, quantum electrodynamics, or QED. In the classical world of Isaac Newton, light was simple. If you shine a light at a mirror, you know exactly where it will go. The angle of incidence equals the angle of reflection. It is a rigid, geometric rule. The light takes the shortest, fastest path. It seems efficient. It seems logical. But Feynman looked at this and asked a question that breaks the human mind. How does the photon know which path is the fastest? Does it have a map? Does it have a calculator? Does it sniff out the path of least resistance before it starts its journey? Feynman's answer, derived from the principles of quantum mechanics, is that the photon doesn't know. It doesn't choose the best path. Instead, with terrifying audacity, the photon takes every possible path simultaneously. This is the concept of the sum over histories. When a photon travels from a lamp to your eye, it doesn't just travel in a straight line. It travels in a curve to the left. It travels in a loop-de-loop to the right. It travels up to the ceiling, bounces off, and comes back down. It travels to the edge of the universe and back. According to QED, the photon explores every single trajectory that is mathematically possible, no matter how crazy or convoluted. It is a chaotic explosion of possibilities. But if light is doing this wild dance, why do we only see it moving in a straight line? Why doesn't the world look like a blur of chaotic light? This is where the speed of light plays its role as the master conductor. To explain this, Feynman used a beautiful, intuitive analogy that requires no complex math, only an imagination. He asked us to imagine that the photon carries a tiny, invisible stopwatch. This stopwatch has a single hand that spins around and around, The speed at which the hand spins corresponds to the frequency of the light, the color. For blue light, it spins faster. For red light, it spins slower. Here is the rule of the game. The stopwatch starts ticking the moment the photon leaves the source, and it stops ticking the moment the photon hits the detector or your eye. When the photon arrives, the hand on the stopwatch is pointing in a specific direction, say 12 o'clock or 3 o'clock. This final direction is what Feynman called an arrow, or in technical terms, a probability amplitude. Now, think about the relationship between the path, the time, and the speed of light. Since the speed of light, sc, is constant, the time it takes to travel a path depends entirely on the length of that path. A short path takes less time, a long path takes more time. And because the stopwatch is spinning incredibly fast, even a tiny difference in travel time will result in the stopwatch hand pointing in a completely different direction when it arrives. Let's apply this to our mirror. Imagine the classic path, the one that hits the middle of the mirror and bounces to your eye. This is the shortest path. The stopwatch ticks a certain number of times, and the arrow lands pointing, let's say, up. Now, consider a path slightly to the left of that sweet spot. It is a tiny bit longer. Because it takes a fraction of a femtosecond longer to travel, the stopwatch spins a little bit more. The arrow lands pointing slightly to the right. Now consider a path slightly to the right of the center. It is also a tiny bit longer. The arrow lands pointing slightly to the left. Feynman's insight was this: to find out what actually happens in reality, you have to add up all these arrows. You take the first arrow, then put the tail of the second arrow at the head of the first, and so on, creating a long chain. Here is the magic. For the paths near the perfect center, the differences in length are so microscopic that the time differences are negligible. The arrows all point in roughly the same direction. They line up. When you add them together, they build a massive, long arrow. This represents a high probability. This is why we see the light bouncing off the middle of the mirror. But what about the crazy paths? What about the path where the photon hits the far edge of the mirror? That path is much longer. The stopwatch spins millions of extra times. But here is the catch. A path right next to that crazy path is also long, but the difference in length is significant enough that the stopwatch ends up pointing in the opposite direction. One arrow points up, the neighbor points down. One points left, the neighbor points right. Because the crazy paths are so sensitive to distance, the arrows are randomized. They are a chaotic jumble. When you add 1,000,000 arrows pointing in random directions, they cancel each other out. They sum to zero. This is the punchline of QED. The reason light appears to travel in a straight line is not because it only travels in a straight line. It is because all the other paths destroy themselves. The universe is a vast democracy of paths, but the weird paths vote against each other, leaving only the sensible path to win the election. The straight line is not a law. It is the survivor of a quantum massacre. So, where does the speed of light fit into this? The speed of light is the constant that dictates the relationship between space and time. It determines exactly how much time it takes to travel those paths. If the speed of light were different, if it were fluctuating, or if it were infinite, the synchronization of the stopwatches would fail. The delicate interference pattern that cancels out the chaos would break down. The straight line would dissolve. We wouldn't see a sharp image in the mirror. We would see a fuzz of probability. The speed limit, c, is the tension in the string. It ensures that the phase of the photon, the spinning hand, is tightly locked to the distance it travels. It forces the universe to adhere to the principle of least action. Nature loves efficiency, not because it chooses it, but because the mathematics of waves eliminates the inefficient options. The speed of light is the filter. It is the mechanism that purifies the chaos of quantum potential into the singular, sharp reality we experience. This view of the world is profoundly different from the rigid box of Einstein or the mechanical clockwork of Newton. It paints a picture of a universe that is constantly sniffing out all of space-time. Every single photon that hits your retina has, in a quantum sense, tasted the edge of the Andromeda Galaxy and the surface of Mars. But those flavors cancelled out, leaving only the light from your computer screen. The speed of light is the strict referee of this game, ensuring that the cancellation happens precisely, maintaining the illusion of a solid, deterministic world. Feynman's arrows also reveal why the speed limit is so fundamental to interaction. These arrows are not just about movement, they are about events. In QED, the interaction between two electrons, the force that keeps your hands from passing through your desk, is mediated by the exchange of photons. These virtual photons are also playing the game of arrows. They are testing every path, every time frame. The speed of light limits how quickly these arrows can spin and how far they can reach before the probability drops to zero. The strength of the electromagnetic force, the very structure of atoms, relies on the fact that c is a finite number. If c were infinite, the stopwatch would never tick, time would be zero, the phase would never change, and the interference that builds our reality would vanish. We are left with a mind-melting realization. The speed of light is not just about how fast a signal moves. It is the refresh rate of the probability calculation. It is the speed at which the universe resolves the question, where is the particle? It computes the sum of histories at the speed of light. The limit is the processing speed of the quantum computer we live in. This leads us to an even stranger territory. We have looked at light moving through space, but in Feynman's diagrams, the math allows for something even more forbidden. If we look closely at the equations of QED, there is no rule that says the arrows must always point forward in time. The math of the speed of light works just as well if you reverse the sign of und. This opens the door to the most radical idea in Feynman's arsenal. The possibility that what we call antimatter is simply normal matter that has broken the temporal speed limit and is flowing backward against the stream of time. To understand this, we must turn the arrow around and look at the universe in reverse. We have reached a point in our journey where the ground beneath our feet begins to dissolve completely. We have accepted that the speed of light acts as a cosmic speed limit, a prison of infinite mass, and a quantum conductor that filters reality. But Richard Feynman, armed with the equations of relativity and his diagrams, found a trapdoor in this prison. It is a trapdoor that does not lead to a faster speed, but to a different direction entirely, not in space, but in time. This is where the concept of the speed limit transforms from a physical barrier into a metaphysical mirror. To understand the true nature of the limit, we must confront the most mind-bending interpretation of quantum mechanics. The idea that antimatter is not a separate substance, but normal matter traveling backward in time. To understand this, we must first look at the problem that plagued physics in the early 20th century. Paul Dirac, one of the fathers of quantum mechanics, had written an equation that successfully combined quantum mechanics with special relativity. It was a masterpiece. But the math had a bug. The equation predicted that for every particle, like an electron, there must exist a mirror particle with the same mass but opposite electric charge. At the time, no such particle had ever been seen. It seemed like a mathematical ghost. Eventually, the particle was discovered, the positron, but the question remained, what is it? Why does nature need a mirror image? Why do we have matter and antimatter? Common sense tells us that a positron is just another type of brick in the universe. A red brick, to the electron's blue brick. They are enemies. If they touch, they annihilate each other, exploding into pure energy. But Feynman looked at the space-time diagrams, the maps we draw to track particles, and he saw something simpler, more elegant, and infinitely more bizarre. He realized that mathematically, there is absolutely no difference between a negatively charged electron moving forward in time and a positively charged positron moving backward in time. Let's visualize this. Imagine you are watching a movie of a billiard table. You see a white ball, an electron, rolling from left to right. Now, imagine you play the movie in reverse. The ball rolls from right to left. But in the quantum world, electric charge is linked to the flow of time. If you reverse time, you reverse the current. So, if you play the film backward, the electron doesn't just move backward, it effectively flips its charge. It behaves exactly like a positron. Feynman proposed that we stop thinking of them as two different particles. Instead, think of them as the same car driving on a road. When the car is driving north, forward in time, we call it an electron. When the car makes a U-turn and drives south, backward in time, we call it a positron. This is not just a semantic trick. It solves the mystery of creation and annihilation. In the standard view, when an electron meets a positron, they destroy each other and become light, gamma rays. In Feynman's view, no destruction happens. The electron is simply traveling forward in time. It hits a point where it interacts with a high-energy photon, and that interaction knocks it so hard that it turns around. It bounces off the wall of the present and starts traveling backward into the past. To us, the observers trapped in the forward flow of time, this single event looks like two separate things. We see an electron moving forward. We also see a positron moving forward, which is actually the electron moving backward. They meet, and suddenly they vanish, leaving only light. We call it annihilation. But from the electron's perspective, it just turned a corner. It didn't die. It just changed its direction through the fourth dimension. So, how does this relate to the speed of light? The speed of light is the barrier that separates forward from backward. In the geometry of Minkowski spacetime, the map Einstein gave us, there is a strict zone called the light cone. Everything, traveling slower than light, stays inside the cone, moving forward into the future. But if you were to break the speed of light, if you were to pierce the skin of that cone, the mathematics suggests that you would no longer be moving forward in any meaningful sense. You would begin to move backward through time relative to other observers. This is why the speed limit is so terrifyingly absolute. It isn't just preventing you from going fast, it is preventing you from reversing the narrative of the universe. The barrier of C is the reason cause comes before effect. If you could go faster than light, you could, in theory, outrun your own timeline. You could perform the Fineman maneuver. You could turn around. This leads to the one-electron universe theory, a concept famously discussed by Feynman and his mentor, John Archibald Wheeler. It is perhaps the most staggering thought in the history of physics, and it relies entirely on this relationship between light speed and time reversal. One day, Wheeler called Feynman in a state of excitement and said, "Feynman, I know why all electrons have the same charge and the same mass." Feynman asked, "Why?" Wheeler replied, "Because they are all the same electron. Consider the implications. If an electron can move forward in time to the end of the universe, turn around, travel backward to the Big Bang, turn around again, and repeat this process trillions of times, it would stitch a massive tapestry through space-time. At any given moment, like now, if you took a slice of the universe, you would see this single thread passing through the slice billions of times. Half of those passes would be going forward, electrons, and half would be going backward, positrons. While this theory has holes, we see far more electrons than positrons in the universe. The logic holds firm within the bounds of relativity. The speed limit is the loom upon which this tapestry is woven. The speed of light is the tension in the thread. It defines the angle at which the thread can turn. The particle cannot just jump from here to there instantly. It must travel through the medium of space-time, obeying the speed limit of interaction. This perspective shifts our understanding of reality from a collection of objects to a collection of events. The electron is not a little ball, it is a world line, a streak through space-time. The speed of light is the rule that dictates how that streak can bend. When we see a particle pop into existence out of the vacuum, we are seeing the thread entering our time frame. When we see it disappear, we are seeing it leave. The vacuum is not empty, it is a crowded station of these world lines, zipping back and forth, appearing and disappearing as virtual particles. This mind-melting logic also clarifies why light speed is a misnomer. Light, photons, exists exactly on the edge. A photon does not experience time. It does not move forward or backward. It exists on the boundary line between the electron and the positron. It is the mediator. In Feynman diagrams, when an electron turns around in time, becoming a positron, it must emit or absorb a photon to do so. The photon is the kick that causes the U-turn. This means that light is the currency of time travel. The interaction that allows a particle to reverse its temporal direction is an interaction with the speed limit itself. This effectively means that the speed of light is the horizon of causality. If you are a massive particle, you are forced to experience time in one direction because you cannot reach the horizon. You are stuck on the forward slope. But if you could touch the horizon, time would stop. And if you could cross it, time would reverse. The limit is therefore the definition of history. Without the limit, there is no history. There is no sequence. There is just a chaotic jumble of events with no order. When we look at the universe through Feynman's eyes, we see that the stability of our existence hangs by a thread, or rather, by the inability to break the speed of light. If we could build a ship that defied sea, we wouldn't just be exploring space. We would be becoming antimatter. We would be reversing our biological clocks. We would be uneating our meals and unsaying our words. We would become ghosts traveling against the current of the cosmos. This insight melts the mind because it removes the arrow of time from the particle itself. The electron doesn't care about time. It doesn't know what year it is. It only knows the path. The flow of time is an illusion created by our collective inability to turn around. We are like drivers on a highway with no exits, forcing us all to drive toward the future at a steady pace. The speed of light is the guardrail that prevents us from making a U-turn. But what if we could break the rail? What if we could send a signal faster than light? Feynman's diagrams show us that sending a signal faster than light is mathematically equivalent to sending a signal into the past. And this brings us to the most dangerous paradox of all. It is not just about strange particles or time-traveling electrons. It is about the murder of logic. If the speed limit is broken, the universe doesn't just get weird, it gets impossible. We must now confront the assassin paradox, the death of causality, and the realization that the speed of light is the only thing protecting the universe from destroying itself in a logical apocalypse. We have seen the electron go backward. Now let us see why we must never follow it. We have arrived at the most dangerous precipice of our investigation. So far, we have discussed the speed of light as a physical barrier, a wall of infinite energy that prevents massive objects from accelerating, and a quantum sieve that filters the chaos of particle paths. These are mechanical limits. They act like the governor on an engine or the thickness of a prison wall. They are frustrating, but they feel like engineering problems. If that were all there was to it, we might still dream of finding a loophole, a wormhole, or a warp drive to cheat the system. But there is a final, terrifying reason why the speed limit exists, and it has nothing to do with mass, energy, or engines. It has to do with the story of the universe itself. If you were to break the speed of light, you would not just be moving fast, you would be murdering logic. You would be destroying the fundamental architecture of cause and effect. To understand this, we must confront the concept of causality. In our daily lives, causality is the most obvious thing in the world. It is the rule that says the cause must always precede the effect. You pull the trigger, then the gun fires. You drop the glass, then it shatters. You punch the wall, then your hand hurts. This sequence is linear and non-negotiable. It is the arrow of time that allows us to make sense of reality. It allows science to exist because science is simply the study of causes and their effects. Without this sequence, the universe is just random noise. But here is the catch. Relativity tells us that time is not universal. We learned in the Einstein Box that time slows down for moving observers, but it gets worse. Relativity also tells us that simultaneity is relative. Two events that happen at the same time for me might happen at different times for you, depending on how you are moving. Imagine the universe as a loaf of bread. This loaf represents all of space-time, past, present, and future. What you call now is just a thin slice cut through the loaf, but if you start moving, your angle changes. You cut the loaf at a slant. Your now slice slices into my future or my past. Normally, this doesn't matter. Because we move so slowly compared to light, the angle of our slice is almost identical. We agree on the order of events. We both agree that the glass fell before it broke. But if we introduce something that travels faster than light, let's call it a tachyonic bullet or a superluminal signal, we create a catastrophe. Let's visualize a scenario known as the assassin's paradox. Imagine a sniper, Alice, standing on a space station. She has a rifle that shoots a bullet at twice the speed of light, 2c. Her target, Bob, is standing on an asteroid a light minute away. Alice pulls the trigger. The bullet, traveling at 2c, crosses the distance in 30 seconds. Bob falls down dead. In Alice's reference frame, the sequence is preserved. Cause, trigger pulled at t equals 0, then effect Bob dies at t equals 30 seconds. It seems fine. Fast, but fine. But now, introduce a witness. Imagine Charlie is flying past in a spaceship. He is moving away from Alice and toward Bob at a high percentage of the speed of light. Because Charlie is moving, his slice of space-time is tilted. He cuts through the loaf at a severe angle. According to the mathematics of special relativity, specifically the Lorentz transformation, if Charlie is moving fast enough, the interval between the two events shifts so drastically that the order reverses. From the window of his spaceship, Charlie sees something impossible. He sees Bob fall down dead before Alice pulls the trigger. Let that sink in. This isn't an optical illusion. It isn't a trick of the light delaying the image. In Charlie's perfectly valid reference frame, the event Bob dies physically occurs in the timeline before the event Alice shoots. The effect has preceded the cause. The glass has shattered before it was dropped. If the bullet were traveling slower than light, this reversal would never happen. No matter how fast Charlie flies, the math guarantees that the cause will always come before the effect. The speed of light is the buffer that protects the sequence. But once you go faster than light, you escape the protection of the light cone. You enter a region of space-time where before and after are matters of opinion, not matters of fact. This leads to the true nightmare, the feedback loop. If Charlie sees Bob die before the shot is fired, he could, in theory, send a message to Alice. Let's say Charlie also has a superluminal radio that transmits at 2C. As soon as he sees Bob die, which for him is before Alice shoots, he radios Alice. He screams, "Stop! Bob is already dead, don't shoot." Because the signal is faster than light, it travels back in time relative to Alice. She receives the message before she pulls the trigger. She hears Charlie say, "Bob is dead," so she decides not to pull the trigger. She puts the gun down. Okay, well, is in trife. Now look at the paradox. If Alice never pulls the trigger, then the bullet never flies. If the bullet never flies, Bob never dies. If Bob never dies, Charlie never sees him fall. If Charlie never sees him fall, he never sends the warning message. If he never sends the warning message, Alice does pull the trigger. Bob dies. Charlie sees it. He sends the message. Alice stops. The universe has crashed. We have created a closed causal loop that contradicts itself. It is a logical error in the code of reality. It is a blue screen of death for existence. The moment you allow information to travel faster than light, you allow information to travel into the past. You allow observers to change the past based on the future. This is why physicists are so confident that the speed limit is absolute. It is not because we lack the technology to build better engines. It is because the alternative is a universe that makes no sense. If FTL travel were possible, you could kill your own grandfather before you were born. You could send the winning lottery numbers to yourself yesterday. You could create outcomes without origins. This realization forces us to rebrand the speed of light. We should stop calling it that. Light is irrelevant. Light is just the messenger boy. We should call it the speed of causality. Think of the universe as a massive, sprawling computer network. Every particle is a node in the network. For the universe to run a coherent simulation, the nodes need to update each other. When an electron moves, it needs to tell the electric field around it, "Hey, I moved." That update cannot happen instantly. If it happened instantly, the entire network would synchronize to a single state and nothing could ever change. There must be a latency. There must be a delay. 299,792,458 meters per second is simply the bandwidth speed of the universe's processor. It is the maximum rate at which one event can influence another. This latency is what keeps the past separate from the future. It is the wall that keeps the eggs from unscrambling. Without this limit, every moment in time would collapse into a single, screaming point of contradiction. The reason you can sit there and watch this video, confident that you were born before you die, confident that the sun is shining because of fusion that happened 8 minutes ago, is because of the speed limit. We often look at the speed of light as a limitation, a barrier that keeps us from conquering the galaxy. We mourn the fact that it will take 4 years to send a message to Alpha Centauri, but we should be celebrating it. That delay is the only thing protecting us from chaos. The silence of the void, the long waits between stars, the vast uncrossable distances, these are the structural beams of reality. They ensure that history is a straight line, not a circle. So, the next time you look at a star and think about how long the light took to get to you, do not see it as a lag. See it as a guarantee. That light is old because the universe is preserving the order of events. The assassin paradox teaches us that we are safe from the whims of time travelers and logical contradictions because the speed of light stands guard. It dictates that reality can only unfold one step at a time. It ensures that the story of the universe has a beginning, a middle, and an end, and that the pages cannot be read out of order. But what if there is no story? What if the now is all there is? We have looked at how the speed of light protects the timeline, but now we must shift our perspective to the only thing in the universe that is immune to this rule. We must look at the world through the eyes of the photon itself. For a particle traveling at the speed of light, the paradoxes of time do not exist, because for a photon, time itself does not exist. We are about to enter the perspective of the timeless. We have spent our time together looking at the speed of light from the outside. We have stood on the platform and watched the train go by. We have stood in the laboratory and measured the mass of the proton. We have looked at the causal structure of the universe and seen how the speed limit acts as the guardian of order. But now we must attempt the impossible. We must shed our heavy, massive bodies. We must leave behind the world of ticking clocks and flowing rivers. We must jump into the skin of the photon itself. We are going to ask the question, what does the universe look like when you are the speed limit? To understand this, we have to push the logic of the Einstein Box to its ultimate breaking point. We learned that as you move faster through space, you move slower through time. If you were an astronaut traveling to the nearest star, Proxima Centauri, at 90% of the speed of light, the journey would take about 4 years, according to the people on Earth. But for you, inside the ship, it might only feel like 2 years. Your clock runs slow. Now, push the throttle forward. Go to 99% of the speed of light. The journey still takes 4 years for Earth, but for you, it takes only a few months. Push it to 99.999%. For Earth, the time is the same, but for you, the journey to another star takes a matter of days. Now, let us make the final leap. Let us accelerate to 100%. Let us become light. What happens to the clock? The math of relativity is unequivocal. The clock stops. It doesn't just slow down to a crawl, it freezes completely. The hands cease to move. The tick never becomes a tock. For a photon, time does not pass. This is not a metaphor. It is a literal description of the photon's existence. From the moment a photon is born in the heart of a star to the moment it crashes into your retina, 0 time has elapsed for the photon. Consider the light from the Andromeda galaxy. We look up at the night sky and we see a faint smudge. We say, that light is 2.5 million years old. We say this because, from our perspective, the light left Andromeda before humans walked upright, traveled across the vast, frozen void of intergalactic space, and finally arrived here tonight. We see it as an epic, ancient journey. But if you could interview that photon and you asked it, how was your trip? Did you get bored during those 2.5 million years? The photon would not understand the question. To the photon, there was no trip, there was no duration. The moment it was emitted by a star in Andromeda was the exact same moment it was absorbed by your eye. It was born and it died in the same instant. The 2.5 million years of our history, the rise and fall of empires, the shifting of continents, the evolution of species, all of that happened simultaneously for the photon. It exists in a state of suspended animation, a permanent now that bridges the gap between the emitter and the absorber. But time is only half of the equation. Relativity teaches us that space and time are linked. If time dilates, space contracts. We know that fast-moving objects appear shorter in the direction of motion. As you approach the speed of light, the universe outside your window begins to flatten. The distance to your destination shrinks. At 99% light speed, the distance to Alpha Centauri is not 4 light years, it is a fraction of that. You don't just get there faster, the road effectively gets shorter. So, what happens at 100%? At the speed of light, length contraction becomes infinite. The distance in the direction of motion shrinks to zero. This is the truly mind-melting perspective of the photon. To a beam of light, the universe has no depth. It has no size in the direction it is traveling. The dimension of space collapses entirely. This means that for the photon coming from Andromeda, the galaxy is not millions of light years away. It is right here. It is touching Earth. The starting point and the ending point are superimposed. The universe, to a photon, is a two-dimensional flatland where the emitter and the receiver are kissing. The vacuum of space, which we perceive as a terrifyingly vast ocean that isolates us from the stars, does not exist for light. For light, there is no distance. There is only immediate connection. This creates a profound philosophical shift in how we view reality. We tend to think of light as something that travels, like a car driving down a highway. But from the photon's perspective, it doesn't travel anywhere. It simply bridges a gap that, for it, isn't there. It is the mechanism by which two particles, one in a distant star and one in your eye, exchange energy directly, instantly, across a void that is only real for massive observers like us. Think about what this implies for the history of the universe. The cosmic microwave background radiation, the afterglow of the Big Bang, has been streaming through the universe for 13.8 billion years. We build massive telescopes to catch it, looking back to the dawn of time. But those photons, the oldest things in existence, are still newborn babies. For them, the Big Bang is happening right now. They have not aged a single second since the universe was a hot, dense soup of plasma. They carry the energy of the beginning of time directly to the end of time, skipping over the entire history of the cosmos in a single, breathless instant. This is why the speed of light is the limit. It is not a speed at all. It is a boundary condition. It is the edge of existence. To exist in time, to experience change, to have a before and after, you must travel slower than light. The moment you touch the speed of light, you exit the flow of time. You become timeless. You become geometry. This explains why we, as massive beings, can never reach this speed. It is not just about energy or mass. It is about the nature of consciousness and experience. To be conscious is to experience a sequence of thoughts. One thought follows another. Cause follows effect. This requires time. If you were to reach the speed of light, your consciousness would freeze. You would be trapped in a single, eternal moment. You would be everywhere along your path at once, unable to think, unable to change, unable to be. The speed limit protects us from the void of timelessness. It forces us to live in the slow lane, where time ticks, where hearts beat, and where life happens. Richard Feynman understood this duality deeply. In his view of QED, the interaction between particles is an exchange of these timeless messengers. When you touch a table, the electrons in your hand push against the electrons in the wood. They do this by exchanging virtual photons. To us, this is a force. To the photons, it is an immediate handshake. The stability of matter, the fact that atoms hold together, is built upon these instantaneous bridges of light. The glue of the universe is made of timeless stuff. So, when we ask why is light speed the limit, we are really asking, why is there time? The limit exists because there is a difference between the map and the territory. Light lives on the map, connecting points instantly. We live in the territory, trudging through the mud of distance and duration. Light speed is the ratio between space and time, but for the thing that defines that ratio, neither space nor time has any meaning. This perspective is humbling. It tells us that our perception of the universe as a vast, lonely, empty place filled with distant objects is just a human illusion, a side effect of our mass. If we could see the universe through the eyes of a photon, we would see a web of instant connections, a singular, unified knot of energy where every point is touching every other point. We are separated from the stars only by our inability to move at the speed of causality. But there is one final mystery to solve. We have said that nothing can travel faster than light and that information cannot be transmitted instantly. But quantum mechanics, the very field Feynman pioneered, threw a wrench into this machinery. It introduced a phenomenon that Einstein called spooky action at a distance, entanglement. It seems to suggest that two particles can communicate instantly, faster than light, breaking the cosmic law we just spent so much time establishing. Does quantum entanglement provide a loophole? Can we use the weirdness of the quantum world to break the speed limit and send messages across the universe in a heartbeat? Or is this just another illusion? To find out, we have to look at the final lock on the prison door. We have to look at why correlation is not communication. We have spent the last 8 sessions building a prison. We have constructed the walls with the geometry of space-time, reinforced them with the infinite weight of relativistic mass, and patrolled the perimeter with the paradoxes of causality. We have convinced ourselves that the speed of light is the absolute, unbreakable limit of the universe. But there is a whisper in the physics community, a ghost story that has haunted scientists for nearly a century. It is a phenomenon that seems to defy everything we have just learned. It suggests that two objects, separated by the vastness of the galaxy, can influence each other instantaneously, mocking the speed of light as if it didn't exist. This is the realm of quantum entanglement, or what Albert Einstein famously and derisively called spooky action at a distance. If you browse the science fiction section of any library, or look at the headlines of sensationalist science articles, you will be led to believe that entanglement is the loophole. It is the get-out-of-jail-free card. The promise is tantalizing. If we can entangle two particles, keep one here on Earth, and take the other to a black hole on the other side of the universe, we can snap our fingers here and the particle there will react instantly. No lag, no latency, no speed of light limit. It sounds like the perfect mechanism for a cosmic internet, a way to build an Ansible that allows us to text our friends on Mars in real time. But tonight, we must be the buzzkill. We must dismantle this hope. We are going to explore why quantum entanglement is the greatest magic trick nature ever pulled, and why, despite its spookiness, it absolutely refuses to let you send a text message faster than light. To understand the trap, we first need to understand the bait. Quantum entanglement occurs when two particles interact in such a way that they lose their individual identities and become part of a single quantum system. Imagine two electrons. We bring them together, let them crash into each other, and then separate them. According to the rules of quantum electrodynamics, the very rules Feynman drafted these two electrons are now entangled. They are mathematically linked. We can measure a property of these electrons, called spin, which is essentially their angular momentum. An electron can spin up or down. Here is the rule. Because of the conservation of angular momentum, if the two electrons were created together with zero total spin, they must always be opposites. If one is up, the other must be down. If one is down, the other must be up. The total must always sum to zero. This sounds simple. Like a pair of gloves, if you have the left glove, the other one must be the right glove. But in the quantum world, it is infinitely weirder. Until you measure them, the electrons are not up or down. They are in a superposition of both states at once. They are both up and down simultaneously, existing in a cloud of probability. Now, we perform the experiment. We give one electron to Alice on Earth, and we give the other electron to Bob, who travels to the Andromeda Galaxy, 2.5 million light-years away. For 2.5 million years, these electrons fly apart. They remain in that fuzzy, undecided state. Then, Alice decides to measure her electron. She opens her detector. Click. She finds her electron is spin up. In that exact instant, not a second later, not 2.5 million years later, but instantly, the wave function of the universe collapses. Because Alice's electron is up, Bob's electron in Andromeda is forced, immediately, to become spin down. Across the void, faster than any light beam could travel, the fate of the particle is sealed. If Bob measures his electron 1 nanosecond after Alice, he will guaranteed find it is down. This is the spooky action. It drove Einstein crazy. It implies that space doesn't matter. It implies that the two particles are telepathic, or that there is an invisible wire connecting them that transmits information at infinite speed. If the change happens instantly, haven't we broken the speed of light? Haven't we violated the cosmic speed limit? The answer is yes and no. The collapse happens instantly. The correlation is instantaneous. But, and this is the most important but, in physics information has not traveled. To understand why, we have to look at this from the perspective of communication. What does it mean to send a message? To send a message, you need to be able to control the signal. You need to be able to say, if I send a 1, it means yes. If I send a 0, it means no. Let's go back to Alice and Bob. Alice wants to use her entangled electron to send a message to Bob. She wants to tell him, attack at dawn. She decides that spin up means attack, and spin down means don't attack. She sits at her detector, ready to send the signal. But here is the fatal flaw of quantum mechanics. Alice cannot control the outcome of her measurement. When Alice measures her electron, the result is truly, fundamentally random. Nature flips a coin. There is a 50% chance she gets up and a 50% chance she gets down. She cannot force the electron to be up. Feynman described this inherent randomness as the core feature of nature. You can predict the probability, but you cannot predict the individual event. So, Alice measures her particle. She gets spin down. Instantly, Bob's particle becomes spin up. Now, look at Bob in Andromeda. He sits by his detector. Suddenly, his electron snaps into the spin-up state. Does he know what Alice did? No. Does he know that Alice wanted to send a message? No. All Bob sees is a random electron that happens to be spin-up. He has no way of knowing if his electron is spin-up because Alice measured hers as spin-down, or if his electron is spin-up just because of random chance. For Bob to understand what happened, Alice has to call him. She has to get on a radio, which transmits at the speed of light, and say, "Hey Bob, I just measured my particle, and I got spin down." Only after Bob receives that phone call 2.5 million years later can he look at his data and say, "Ah, so that's why my particle was spin up." This is why correlation is not communication. Imagine Alice and Bob are each given a book of random numbers. The books are identical. Alice looks at page 1 and sees the number 7. Bob looks at page 1 and sees the number 7. They are perfectly correlated. But Alice didn't send the number 7 to Bob. The number 7 was already there, generated by the entanglement. If Alice cannot choose which number appears on the page, She cannot use the book to write a letter. She is just reading a random script, and Bob is reading the complementary random script. They are synchronized, but they are both helpless observers of a random process. Richard Feynman and later physicists like John Bell wrestled with this. Bell proved, mathematically, that what happens in entanglement is truly weird. It isn't just that the particles were pre-programmed, like gloves in a box. The connection is active and non-local. But even Bell acknowledged that this non-locality cannot be used for signaling. This is known as the no communication theorem. It states that no measurement on part of a quantum system can be used to convey information to another observer instantly. The universe is like a very strict lawyer. It follows the letter of the law, even if it violates the spirit. The law says, no information faster than light. The universe says, fine, I will allow the state of the universe to collapse instantly, everywhere at once. I will allow a ghost-like connection between separated particles. I will allow the reality of the electron to be determined non-locally. But I will hide the result behind a wall of absolute randomness so that no useful data can ever cross that gap faster than a photon. The randomness of quantum mechanics acts as encryption. The key to decrypt the message, Alice's result, is held by Alice, and she can only send that key to Bob at the speed of light. Without the key, Bob's data looks like pure noise. It is statistically random. It is only when you bring the two datasets together at sublight speeds and compare them side by side that you see the spooky correlation. You see that every time Alice got up, Bob got down. The pattern emerges in the comparison, not in the moment. So, the quantum loophole is a dead end for starships and galactic empires. We cannot use entanglement to bypass the delay of Mars missions. We cannot use it to trade stocks faster than Wall Street. The speed of light remains the supreme governor of cause and effect. Entanglement tells us something profound about the structure of reality, that the universe is more interconnected and holistic than we thought. That space is not as separating as it feels, but it does not give us a way to break the chains of causality. It seems we are truly stuck. We are massive beings, trapped in an infinite mass prison, protected by a causality paradox, unable to communicate faster than the speed of light, even with the magic of quantum mechanics. The limit is absolute. But as we reach the end of our journey, we must ask ourselves, is this a bad thing? Is being trapped in this bubble of causality a tragedy? Or is it the very thing that makes existence possible? In our final session, we will look at the latency of the universe, not as a flaw, but as a feature. We will see why a universe without a speed limit would be a universe where nothing could ever happen. We have journeyed through the architecture of reality, bumping into the walls of the cosmos at every turn. We started with the conflict between Newton's mechanical intuition and Maxwell's electromagnetic waves. We sat inside the Einstein Box and watched time slow down to a crawl. We pushed against the infinite mass prison, realizing that our own energy weighs us down. We traced the chaotic paths of Feynman's arrows, discovered the time-reversing nature of antimatter, and stared into the abyss of the assassin's paradox, where logic itself comes undone. Throughout this exploration, we have treated the speed of light, this number, 299,792,458 meters per second, as a limit. We have viewed it as a frustration, a cosmic speed bump that keeps us trapped in our solar system, preventing us from exploring the galaxy like the heroes of our science fiction stories. We have asked why, with a tone of complaint. Why is the universe so slow? Why is the cage so tight? But in this final analysis, we must flip the script completely. We must stop looking at the speed of light as a limitation and start seeing it for what it truly is: the processing speed of the universe. If we view the cosmos not as a collection of objects, but as a massive, sprawling information network, a computer of infinite complexity, then the speed of light is not a speed limit for travel. It is the latency of the system. It is the clock speed of the central processor. It is the fundamental update rate at which reality calculates itself. Imagine for a moment that the universe is a grid. Every point in space is a node in this grid. These nodes contain data, the strength of the electric field, the curvature of gravity, the presence of matter. For the universe to happen, these nodes must talk to each other. If an electron moves in node A, it must communicate that change to node B, so that node B can adjust its electric field accordingly. This communication is not magic, it is a physical process. The message must traverse the distance between the nodes. The speed of light is simply the maximum speed at which this handshake can occur. It is the time it takes for one patch of space to say to its neighbor, "Something changed over here, you should update your status." If we look at it this way, we realize that light is just the most visible courier of this information. Gravity travels at this speed. Gluons travel at this speed. Gravitational waves, the ripples in the fabric of space-time itself, travel at this speed. It is the speed of interaction. It is the speed of news. When a star explodes 1,000 light-years away, the news of that explosion expands outward in a sphere. Until that sphere hits us, as far as we are concerned, the star is still alive. The universe has not yet updated our sector of the grid. We are living in a local version of reality that is waiting for the download to complete. Now, consider the alternative. This is the thought experiment that redeems the limit. What if the speed of light were infinite? What if Newton was right? In a universe with infinite processing speed, interaction would be instantaneous. Every point in space would be in constant, immediate contact with every other point in space. If you moved an electron in your finger, every proton in the Andromeda galaxy would feel the push instantly. There would be no lag. There would be no latency. At first glance, this sounds efficient, but in practice, it would be a catastrophe. If gravity acted instantly, the entire universe would likely collapse into a single point in a fraction of a second. Every mass would pull on every other mass with zero delay, creating a runaway crunch. If light moved instantly, the night sky would not be black. It would be a blinding wall of white fire, because the light from every star in the infinite history of the universe would arrive at your eye simultaneously. This is known as Olber's paradox, and the finite speed of light is one of the solutions. An infinite speed universe is a universe where everything happens at once. All energy, all matter, all history would be compressed into a single, screaming instant of infinite density and infinite brightness. There would be no time for structures to form. There would be no time for planets to cool, for life to evolve, for thoughts to be thought. The delay is the gift. The latency is what allows the universe to unfold. Because it takes time for gravity to propagate, solar systems can stabilize. Because it takes time for light to travel, we can have a dark sky at night, allowing the heat of the Earth to radiate away, keeping our planet habitable. The speed limit creates separation. It allows here to be different from there. It allows now to be different from then. It carves out a protective bubble of local causality around us. It ensures that we are not overwhelmed by the collective noise of the entire cosmos. We are insulated by the vast distances and the slow speed of information. We enjoy a quiet corner of the universe because the news from the rest of the galaxy takes eons to reach us. This rebranding of the speed limit as Latency also resolves the tension between the quantum and the classical. We saw with Feynman's arrows that the universe is probabilistic. It is a game of chance. But the speed of light imposes a strict order on how those chances resolve into reality. It creates a causal cone for every event. It dictates that the past is fixed, the future is open, and the present is the razor's edge where the calculation is happening. The speed of light is the speed at which the present writes the history. It is the speed of the narrative. When we look at a computer rendering a video game, we know that if the processor tries to do too much at once, the frame rate drops, the game lags. But the universe never lags. It maintains a perfect, constant frame rate. It sacrifices space and time to maintain this rate. As we saw, if you try to go too fast, the universe shrinks your space and slows your time. It distorts the geometry of the simulation to ensure that the update rate remains constant. It is a self-correcting code that prevents the system from crashing. The infinite mass prison we discussed is just the system preventing a buffer overflow. It prevents any single object from requiring infinite processing power. This perspective brings a sense of peace to the human condition. We often feel insignificant when we look at the stars, tiny specks of dust on a rock, separated from our neighbors by uncrossable voids. We lament that we will never meet aliens, never stand on the surface of an exoplanet, never outrun our own mortality. But we should realize that this isolation is structural. It is necessary. The void is not empty. It is the insulation that keeps the wires from short-circuiting. We are trapped in a bubble of causality, yes. But that bubble is our home. It is the only place where life can exist. Life is a process. It is a sequence of chemical reactions, neural firings, and cellular divisions. All of these require a sequence. Cause must lead to effect. If the speed of information were infinite, there would be no sequence. There would be no process. Life, which is fundamentally a story unfolding in time, would be impossible. We exist because of the limit. We are the children of the lag. So, the next time you switch on a light, do not think of it as a beam traveling through space. Think of it as the universe updating its database. When you look at the moon, you are seeing the moon as it was 1.3 seconds ago. You are looking at a slightly outdated version of reality. When you look at the sun, you are seeing an 8-minute-old ghost. When you look at the stars, you are looking into deep history. We are never truly seeing the now of the universe. We are always looking at the past, waiting for the latency to catch up. And this is beautiful. It means that the universe is a grand tapestry of events woven together by these threads of light. The delay allows the tapestry to have a pattern. It allows for complexity. It allows for mystery. The limit that Newton hated, that Maxwell discovered, that Einstein explained, and that Feynman drew, is the fundamental constant of order. The war between Newton and Maxwell is over. The paradoxes are resolved. We accept the terms of our existence. We accept that we are massive creatures who must move slowly through the dark. We accept that we can never touch the ceiling of reality, where the photons dance in timeless abandon. But in exchange for our slowness, we get to have a story. We get to have a past, a present, and a future. We get to have a universe that makes sense. The speed of light is not a wall. It is the heartbeat of the cosmos, ticking away at a steady, unyielding rhythm, ensuring that everything happens exactly when it is supposed to, not a moment sooner, not a moment later. It is the law that keeps the chaos at bay, and for that, we should be grateful. We are safe in the slow lane, watching the light go by, living in the precious, protected lag of a universe that takes its time to be real. Good night, and I'll see you in the next video.